So we've been talking about the younger Dryas events.
Yep.
That's what we were talking about. I remember now. It's all coming back to me. So, yeah, interesting times. And I would think that getting more knowledge out there, more people looking at this period of time is going to be valuable. We need a lot of perspectives on this because it's still not explained yet. There's too many unexplained variables. Bolide impact seems almost certain, but were there other factors? Could there have been a solar factor? I think that's very plausible, and we should certainly explore that as a possibility, because I don't rule out Robert Schoch's ideas. I don't necessarily think it's an either or, actually. I think it's perhaps we're looking at a series of episodes stretching over that 14.6 to 11.6 thousand years ago, centered around 12.9, but it could have been a multiplicity, a very complex series of events that peaked at 12,009, because 12,009 is when we find the impact proxies. But at 14.6, this is the dating for meltwater pulse 1A. Now, if that dating is correct, if it's correct, then that means that there was something that happened that injected enough energy into the system to melt copious amounts of glacier ice sheet that's then returned into the ocean basins and causes this first big pulse of sea level rise. What caused that? Was that impact an earlier impact? Were the traces of such impact have been lost or just haven't been found? Or was it something solar or something we haven't even begun to imagine yet? But the point is that at 14.6, at 12.9, and 11.6, we seem to have highly energetic events. At 12.9, we have impact proxies. To my knowledge, we do not have impact proxies at 11.6 or 14.6. But something nevertheless had to have happened, because you don't just suddenly melt, a few 100,000 cubic miles of ice over a very short period of time without some source of energy that's going to trigger that melting. And that is the question: what was the source of that energy? However, at 12.9, we do have this growing body of evidence that suggests the ET component in the form of the proxies we've been talking about, the nanodiamonds, the magnetic grains, the microspherules, the platinum and iridium deposits that are being found in ice, the soot, the carbonized layers that suggest extraordinary biomass burning. So how do you explain biomass burning? Well, could it be the sun? I don't know. I don't know if this, again, there's so much new information coming out every year on so much of this stuff, particularly like solar physics and the role of the sun. It's hard to keep up with it all. But there certainly is growing evidence that the sun is a highly variable star, a lot more variable than anybody had assumed, back 25 or 30 or 40 years ago. In fact, most of the 20th century was the solar constant. But the question is that can small variations in radiative output of the sun be somehow amplified through some kind of positive feedbacks? And that's one of the major questions under discussion right now. But we certainly do know that there's debris out there. We know there's comets. We know there's asteroids. We know that we've had close encounters repeatedly. We've had close encounters just within the last few years, right? So this is nothing too exotic to invoke the idea that there are actual impacts into the Earth on a fairly regular basis. Now, one would assume from the scale and magnitude of these, what we've seen recently is that these objects are not going to be enough that we've seen recently would not be enough to cause a global catastrophe. Global catastrophe, we're probably looking at least a half a mile in diameter, probably more like a mile above. A mile would be disastrous, perhaps on a continental scale. Would it be disastrous on a planetary scale? Well, it may not be disastrous to where it would essentially wipe out biological life like you would have in the epicenter of a you know, basically wherever, if you had a kilometer or a mile sized asteroid or piece of a comet nucleus striking the ground, right? Say it's a mile in diameter. Well, that's going to pretty much sterilize everything, probably for somewhere around a radius of 500 miles. And then beyond that, you know, the magnitude of the destruction would begin to fall off. If you're on the opposite side of the Earth, you could probably survive. Unless, of course, you had a seismic wave that traveled around the planet and then converged at the antipode of the impact. Now, that's a possibility that has actually been proposed relative to the Cretaceous Tertiary impact, because the impact site in the Yucatan would have been directly opposite the point that looks very close to the outflow of the Deccan Traps in India. The Deccan Traps was one of course, the great volcanic events in the history of the Earth that is oftentimes blamed for the extinction of the dinosaurs. And that's been one of the ongoing controversies between regarding to the KT extinctions, which, by the way, is not KT anymore. Now it's KP, the Cretaceous Paleogene. You know, and I'm having a tough time with that, because for 30 years I think KT. Now all of a sudden they want me to change to KP, the Cretaceous Paleo. See, it's difficult enough because Cretaceous starts with a C, but we're using the letter K, right? Well, that's because we're already using the letter C for the Cambrian. So we couldn't use the letter C again, or otherwise it would be very confusing. So they used the letter K, which probably in Latin, creta, which means chalk, probably started with a K, is what I'm going to guess. But in any case, the KT boundary is now the KP boundary. So anybody who is actually trying to do research, don't get confused. It's the same boundary. The KT is the KP. It's where the dinosaurs went extinct, and where it's almost 100% verified now that there was a huge impact that left a giant buried crater flanking the Yucatan Peninsula, roughly 66 million years ago. But on the other side of the Earth, you had the Deccan Traps, and the Deccan Traps were just belching out billions of metric tons of sulfate aerosols into the Earth's atmosphere, which would have all kinds of drastic consequences. So my take on it is that, again, it's not an either or thing. I mean, and I don't know, and nobody knows for sure, because of the dating resolution is not fine enough to determine, was the Deccan Traps volcanism, that episode, a consequence of the impact? It has been proposed that the shock wave of that impact might be enough to induce these massive plume volcanisms that we see. Because when we go back to the Permian Triassic of 241 million years ago, what do we find there? We find that there was the huge volcanic outflow that left the Siberian Traps, which is, again, one of the gigantic magmatic events in the history of the Earth. And of course, that correlates with the greatest mass extinction on Earth, where 90 to 95% of all species in the oceans went extinct, and something like 80% of all land species bit the dust. That was, it has been said, that was the closest that life came to being wiped out completely on the Earth, was that Permian Triassic. But then we find the Triassic-Jurassic mass extinction, which is one of the Great Five, being associated with the Central Atlantic magmatic plume, which was also a huge outflow. So, but also in each of those big five, there's evidence not as definitive and as conclusive as the evidence you find at the KT boundary, but there is evidence at every single boundary for impacts. So it seems to me that there may be a situation where you have impacts. So you have something from outside the Earth associated with massive volcanism inside the Earth, exogenic, endogenic, coupling together, and it's through the combined effects of the exogenic and the endogenic that you get these really, really massively catastrophic disruptions of the biosphere that leads to a very profound loss of species. And the Great Five, of course, that's what characterizes them. Each one of them is that you've got hugely proliferating species, Ordovician, late Ordovician, late Devonian. You got all kinds of fish in the ocean. You've got things going on, and then boom, over half of all species are gone in a very, very short period of time, geologically speaking. But yeah, I think what we're trying to do here is we're trying to concoct a model that actually involves a whole interrelated series of terrestrial, solar events, even galactic events, because we may have to go to the galactic level really to begin to understand the flux of cometary objects to the inner solar system.
Right. It seems like Robert Schoch's idea that this was a solar, that all of these proxies could have been created by, a natural sort of solar process or something that happened with the sun, CME, what have you.
Mm-hmm.
You have this big, this rogue body come into the inner solar system. The sun causes it to break up. Large, massive pieces of it fall into the sun.
Mm-hmm.
Right. Or maybe, that would be the 14,000-year-old thing is we have the CME. Meltwater pulse 0 or whatever.
Mm-hmm.
Then the next one is an actual impact, which is the beginning of the Younger Dryas. But it's the same body still in orbit. That, and maybe there's this 1,000-year period of after that everything's in flux. Yeah.
How big would something how big would something have to be to trigger a disturbance on the surface of the sun?
Well, surprisingly not that big.
Yeah, I was thinking about Jupiter. I just read a story. I wish I could remember where it was from, but it was about the Shoemaker-Levy 9 impacts. They're still studying the disturbance in the atmosphere.
Mm-hmm.
Really?
From Shoemaker-Levy 9, which was 1994 or something?
Man.
They've been watching. So when it first happened, they're studying these black circular masses where the impacts took place, and then they watched those gases go into the swirls, and it taught us all this stuff about the jet streams and everything going around Jupiter, because they're still following
the heat
those disturbances that are moving around the atmosphere of Jupiter.
Mm-hmm. Mm-hmm.
Yeah, I don't know. That's just crazy. So yeah, I mean, it could have still been one single body. In other words, coming in, being broken up, pieces of it go into the sun. Later, some of it hits us. Later, more of it goes into the sun.
Yeah.
Mm-hmm.
So, I don't know.
Well, Louise K. Hara, who is a solar scientist who studies the sun, wrote back in 2002 a paper that was published in the Philosophical Transactions of the Royal Society of London. It was entitled Explosive Events on the Sun. We are now in the unprecedented position of having access to a number of space observatories dedicated to the sun. The Yoka, if I'm saying that right, spacecraft, SOHO, or the Solar Heliospheric Observatory, the Transition Region and Coronal Explorer, and the Ramat High-Energy Solar Spectroscopic Imager. So these are all satellite technologies that have been deployed, that have been looking at the sun for the last couple of decades. These cover a wide wavelength range from white light to gamma rays with both spectroscopy and imaging, and allow huge progress to be made in understanding the processes involved in such large explosions. The high-resolution data show dramatic and complex explosions of material on all spatial scales on the sun. They have revealed that the sun is constantly changing everywhere on its surface, something that was never imagined before. There are two types of explosive events on the sun: solar flares and coronal mass ejections. Impulse of energy release in solar flares is one of the most dynamic and highly energetic phenomena in the solar system. The process is poorly understood and yet occurs in a variety of contexts in the universe. For example, solar flares, planetary magnetospheres, active galactic nuclei. understanding impulsive energy release is a major goal across a wide range of space physics and astrophysics. Coronal mass ejections, on the other hand, pour 10 to the 13th power kilograms of material into the solar system in one event. Much has been learned over the past 10 years about the working of explosive events and their origin. The ultimate goal now is to understand the actual trigger of these spectacular events. That's it right there, the trigger. What is the trigger?
It's the 10 to the 13th power kilograms of stuff first being picked up into a loop by a magnet and then given escape velocity.
And that 10 to the 13th kilograms would be 10 to the 10th metric tons. If you want to do a quick.
That's just mind-blowing.
Wow.
That is a lot.
That's a lot of stuff.
That's a lot of stuff.
Yeah. Escape velocity from the sun. Yeah.
I don't know. I don't know that number off the top of my head.
I was trying to remember what are the estimated, what's the estimated surface gravity that it's on the sun? I can't remember.
But see, then that gets us to where I think the connection could possibly lie. This was a paper published in 2009 in at the proceedings of the International Astronomical Union Symposium number 257 under the heading Universal Heliophysical Processes. This particular paper was called Explosion of Sun-Grazing Comets in the Solar Atmosphere and Solar Flares. So what this research is doing is showing the correlation of comets being sucked into the sun at extraordinarily high velocities and triggering massive explosions in solar flares and coronal mass ejections. So that's where I think we will pick up. We'll come back to that at some point because it's really important. And I think it begins to unify some of the various models. For example, it resolves, I think, the controversy between impact events and solar flares affecting the Earth during these transitional events 12 to 14,000 years ago, roughly.